Hey guys, and welcome to this video on solving linear inequalities in two variables. So let's make it happen. Alright, remember earlier when we discussed how to solve inequalities that involved just one variable. For example, negative 2x plus 3 is greater than or equal to negative 13, or negative 3x minus 5 is less than negative 23. So why don't you take a second to pause the video. Please solve each of these inequalities and graph them on the number lines below. Alright, now note that in each case, we graph the solution set to the inequalities by shading what I'll call half of the real number line. In each case, there was a number that acted as a boundary of sorts between all numbers that were solutions to the inequality and those that weren't. In the first example, that number was 8. In the second example, that number was 6. Note, of course, we filled in the 8 because that was part of our solution set because it was x is less than or equal to 8. 6 we left not filled in because it wasn't part of our solution set because it was x is strictly greater than 6. Also earlier, we discussed compound inequalities, where we had two inequalities involving the same variable at the same time. For example, negative 2x plus 3 is greater than or equal to negative 13, and negative 3x minus 5 is less than negative 23. And in this case, we were looking for numbers that made both of these statements true at the same time. And we did this by graphing each of them individually on the same number line and seeing which numbers were shaded twice. Those numbers would represent solutions to both of the individual inequalities and thus the compound and inequality. In this section, we're going to be solving very similar inequalities, only now our inequalities are going to involve two variables. For example, 3x minus 4y is less than or equal to 12. And now we're looking for ordered pairs of numbers x comma y such that when we substitute both numbers in for the respective variables, we get a true statement. So can you think of any ordered pairs that would make that statement true? How about 1 comma 5? Awesome, that one worked. What about negative 3 comma 2? That ordered pair also worked. What about 4 comma negative 7? So the ordered pair 4 comma negative 7 doesn't work. Of course, there are going to be infinitely many ordered pairs that we can come up with that will make that inequality true. And so it wouldn't make sense for us to list all of them. The best way to capture all of them will be to create a graph. Now, unlike before, when our inequalities had only one variable and we could graph the solutions on a one-dimensional number line, now our inequalities are going to have two variables. So we will need to graph them on a two-dimensional plane. Alright, now we've got two main strategies for graphing these sorts of inequalities. And the first strategy is to solve for y, or solve for the dependent variable. And note, all of the same properties of inequalities that we talked about before are going to apply. For example, if we multiply or divide both sides of this inequality by a negative number, we're going to have to switch the direction of that inequality for it to remain true. So why don't you pause the video and solve this inequality for y. Alright, so we're just trying to graph y is greater than or equal to negative 3 plus 3/4 x. Now, before we graph this inequality, let's first graph what's called the boundary line. Remember before when we were graphing inequalities in one variable, 8 and 6 were kind of the boundaries between numbers that were solutions and those that weren't solutions. And the boundary line of an inequality in two variables is the line that separates ordered pairs that are solutions from those that aren't. And to find a boundary line for an inequality in two variables, all we have to do is simply replace the inequality sign with an equal sign. So the boundary line in this case will be y equals negative 3 plus 3/4 x. And I'm wholly confident in your ability to graph that, so why don't you graph that right now? Alright, so there's our boundary line, and I really strongly suggest labeling your boundary line when you draw it. Now, note that since our equation is y is greater than or equal to negative 3 plus 3/4 x, the ordered pairs on this boundary line are included in our solution set, because for each of those ordered pairs, the y value is exactly equal to negative 3 plus 3/4 x. And so that's why we draw a solid boundary line, to show that these ordered pairs are part of the solution set. This is the exact same thing as drawing in a filled-in circle before, when we had x is less than or equal to 8. Now, if this were not the case and we had y is strictly greater than, we would not graph a solid line, and we would do something else to show that the boundary line is not included in the solution set. We're going to see that in the very next example. Now, just like with inequalities in one variable, where we either shaded left or right of the boundary number, now we are going to shade above or below our boundary line. But how do we know which side to shade on? So what we've got here is a graph of our boundary line, y equals negative 3 plus 3/4 x. And we have a point on that boundary line. And in green, we see an expression showing our y value and what negative 3 plus 3/4 our x value is. And of course, for any point on this line, the y value is going to be exactly equal to negative 3 plus 3/4 the x value. That's what it means to be on that line. But for any point above the boundary line, the y value will be greater than negative 3 plus 3/4 times the x value. For instance, consider these 2 points. The x coordinates are the same, they're both negative 4, and of course, in our point in green, negative 6 was exactly equal to negative 3 plus 3/4 the x value. So in our point in red, of course, negative 3 is going to be greater than that. Or for these two ordered pairs, for the ordered pair in green, 3 was exactly equal to negative 3 plus 3/4 times 8. So of course 5 is greater than negative 3 plus 3/4 times 8. And for any point above our boundary line, it will always be the case that y is greater than negative 3 plus 3/4 x. Of course, for any point below our boundary line, it will be the case that y is less than negative 3 plus 3/4 x. And in general, if when you solve for y, your inequality looks like y is greater than, or y is greater than or equal to, shade above the boundary line. And of course, this is true whenever you solve for your dependent variable, whether or not it's y. And if your inequality looks like y is less than, or y is less than or equal to, we'll shade below the boundary line. So when we're graphing these inequalities by hand, my suggestion is to shade 1/2 of the plane kind of like this. And this graph represents all of the solutions to the inequality y is greater than or equal to negative 3 plus 3/4 x, or the inequality 3x minus 4y is less than or equal to 12. Alright, now there's a second strategy for graphing these inequalities, and it starts by graphing the boundary line however you would like, so not necessarily putting this in a slope-intercept form. Now remember, the boundary line happens when we replace the inequality with an equal sign, so just graphing 3x minus 4y equals 12. So if we don't want to put this in a slope-intercept form, maybe we could graph it by finding the intercepts. Great, so we've got our same boundary line as before, but since we don't have this inequality in nice y is greater than or y is less than form, we don't yet know whether to shade above or below it. Well, here's my claim. It's either going to be the case that all of the ordered pairs above this line are solutions, and all the ones below are not, or the opposite, where all the ordered pairs below this line are solutions, and all of the ones above are not. So all we have to do is test one point that's just not on the boundary line. And if it works, we shade that side of the line. And if it doesn't, we shade the other side of the line. Now here's my question. What do you think a good ordered pair is to try? Well, my favorite ordered pair to test is the ordered pair 0, 0. And we probably don't even have to write anything down. We can just look at this inequality and say, will 0, 0 make this inequality true? Absolutely. And if we know that point works, that means that every ordered pair on that side of the boundary line is going to be a solution, so we know to shade above the boundary line. And that's our second strategy for graphing these inequalities with two variables. Alright, now let's graph all of the solutions to the inequality negative 3m plus 2k is greater than 18. Two big differences. The obvious one is we're not using x and y anymore, we're using m and k, so let's let m be our dependent variable, k be our independent variable, and we're dealing with an inequality where we have something as strictly greater than 18, and not greater than or equal to. Of course, the first thing we want to do is graph the boundary line. But before we graph that boundary line, you kind of have to choose which strategy you're going to take first. I'm going to take the first strategy. I'm going to solve this inequality for m and then replace the inequality with an equal sign. So once I get the boundary line, I'll know exactly whether to shade above or below. Okay, now we know that once we graph the boundary line, we're going to shade all the ordered pairs below it because when we solve for our dependent variable, we got m is less than negative 6 plus 2/3 k. But note that the ordered pairs on the boundary line are not going to satisfy our inequality because if you're a point on the boundary line, it'll be such that m equals negative 6 plus 2/3 k. So how do we tell the reader that the points on the boundary line are not solutions to the inequality? We're not going to draw a solid line anymore. Now we're going to draw a dashed line. And drawing a dashed line here is exactly the same as when we used to draw an open circle on a number line to show that that boundary number wasn't part of our solution set. And now we know to shade below our boundary line. Alright, so here are two problems to practice with. So why don't you pause the video and please graph all of the solutions to these two inequalities and then unpause and we'll see how it went. So here are two interesting looking inequalities because each of them involve only one variable, but we're asked to graph them on a two-dimensional plane, which is usually for inequalities with two variables. So for x is less than or equal to 4, if we had just a one-dimensional number line, we would know exactly how to graph this. You put in a full circle at 4 and you shade to the left on the number line. So how do we graph this if we have a plane with two variables? Well, note that x is less than or equal to 4 is kind of the same thing as saying x plus 0y is less than or equal to 4. Now to graph this, let's start by graphing our boundary line, which of course happens when we replace the inequality with an equal sign. So our boundary line in this case is just x equals 4, and we definitely know how to graph that. And of course, that's going to be a solid boundary line because this is a less than or equal to inequality. Now, there are two ways to go from here. The first is, since x is less than or equal to 4, we know we're going to shade to the left of the boundary line. If it were x is greater than or equal to 4, we'd shade to the right. Equivalently, we could try a test point. How about 0, 0? If we substitute 0, 0 in for the variables in this inequality, it's obvious that that makes the inequality true. So we're going to shade on the side of the boundary line that contains the point 0, 0. All right, and there's our graph. What about y is greater than negative 6? Now, if we're going to try and graph this on a plane, which is usually reserved for inequalities with two variables, we could consider this y plus 0x is greater than negative 6. Of course, our boundary line in this case is going to be y equals negative 6. And this is going to be shaded because, of course, this is a y is greater than and not y is greater than or equal to inequality. And of course, because our inequality is greater than, we know to shade above the boundary line.